All right. Hello, what's good, guys? I'm Soham, that's Samra. Welcome to our third Pioneers meeting here at Big Think AI. This will be a continuation of the data science lectures that we've been doing since last week. Last week, as I said, we were focusing more on helper methods and the more nitty-gritty of how you do data science. Here we'll be looking at a more bird's eye view and seeing what a completed data science project looks like. Please don't account this.
Would you like me to?
Yeah, please.
What do you think? Just say next slide, please, and I'll get it up.
Okay. You got something. You got something.
Oh yeah, let's do this thing. Can you just click a little bit so that actually the road there? Yeah, that's connections. Okay. I don't
any more?
No, that's it. Yeah, so just to give a little bit of context here, we call ourselves Big Think AI, but we haven't really delved into the AI or machine learning part yet. But just to give you a little insight, the journey we're embarking on here, we are currently in this arena right here, the data collection and process. Thank you.
And yeah,
We're right now talking about data and how to manipulate. It's a very important step, and quite honestly, it does take the majority of the time because of how libraries work and how a lot of these machine learning models are already predefined for us, as you'll see in the case. But yeah, just know that this is a very important step, and that's the reason why we're spending so much time on this for the actual machine learning models. But yeah, and this isn't exactly related, but someone here might want to mention it. But there is going to be a vacancy in the data science lead position for next semester because someone is graduating this December. So I just wanted to put that out there. We are going to be looking for people to fill that position up. There's going to be elections in the winter, hopefully. So yeah, just keep that in mind. Good resume stuff. Yada yada yada. But yeah.
Bear in mind, you'll have to deal with some around that, so if that's a turn off for any of y'all, this.
Yeah, that's your problem. Good luck.
That's fair. But yeah, other than that, go ahead, Tom.
All right. You finish the slide. So
Yeah.
next slide, please.
Thank you. Hate to say the actual word monkey for this.
Yeah. Okay, so we keep talking about this data science pipeline, but what do we mean by that? So the data science pipeline, as we are using it in this lecture and in this club, is just essentially a set of processes that converts our raw data that we find in the wild into actionable answers to the business questions that we have. And by business questions, we just mean questions we might have about a situation that we might need to solve for, say, a business. Data science is essentially the answer to a question we might have about our data or situation. It's not just the process by which we find out the trends and the solutions, but it's also how we answer the questions we may have. Now, while it is true that individual details and methods and what specifically we do will change from project to project, the general process and the order of the steps that we take in the data science pipeline will generally speaking remain the same. In fact, once you get significant experience, you'll find that the data science pipeline is so generalized and so repeated that you can actually automate the data science process to a certain extent upward. And up here, we just have this nice little visual where we are taking the observation and, oh, could you move the camera this up a little bit?
I can do you one better, honestly.
Thank you. Yes, so essentially, data science, sorry. Okay, you're good. You have this fun little visual where you're taking the observation and data, and also Mario for some reason, and we are using the pipeline to transform those three essential components, obviously, into statistical models that we can use in order to answer questions we might have about our environment. We can also use it to train our own AI models, which we'll get a little bit into later this lecture. Next slide, please.
Mario's not even PhD.
Did not
Are there animations or is it just?
No, there's
Okay.
okay, so here are the 5 main steps about the data science pipeline that we're going to go through today. So step 1 is data collection. We just got to get our data to us in a readable format. Specifically, this will be about gathering relevant data from reputable sources. Those are both the relevancy and reputability reputability, yes, reputability are two main components that I'm going to go a little bit more into later in this slide. Our next step, once we have all our data, is something called data typing. This is because a lot of times when we get data from an online trusted source, it's not made specifically for us, right? It's made for everyone who might need the data. So it's not customized to our specific preferences and needs. So this is something we're going to tackle a bit more here in data typing, where we're going to remove or manipulate the dataset info in order to make sure the data is easier to work with for our specific purpose. This is really important because these specific things that we're going to do in data typing is going to vary greatly based on what we're going to need from our data. In fact, you're going to find in these data science process, it is very common to actually do some data typing, then go to steps 3, 4, and 5, and then realize, oh God, I actually need to do something with the data, but I need to change it, and then you need to go back to step 2 and tidy it even more. Don't be alarmed if that happens, it's very normal. I do it all the time myself. Anyways, step 3 is the exploratory data analysis. This is the main part of the data science pipeline where we're doing the actual analysis of our data. So this is where we cross-reference our data with certain statistical model trends in order to find the said trends. And we will also work to visualize our results for a non-computer science audience. So remember, a big goal of essentially doing this entire pipeline, gathering data, trying to analyze the data, is that we're trying to prove some fundamental thesis or point to a larger audience, not just the people around us who are also, comp sci nerds like, or info sci nerds, or computer nerds like the rest of us, right? So this is actually a very, very important step in taking the trends we find and being able to convey them to a mass audience. Step 4, we're not going to get too much into this, but it's called AI modeling, which is just selecting, training, and improving on AI models made for our specific data. And yes, it's true, it's called Big Think AI. But in fact, because we believe AI is so important, we're going to save this step for another lecture where we'll have more time to go more in depth into it. Although I'll cover a little bit in this lecture. Finally, step 5, we're going to draw conclusions from the data in the previous 4 steps. And so essentially, this is continuing what I was mentioning in step 3 of making our trends understandable to a wider audience. So we're going to use all the information from the above 4 steps. Sorry. We'll even go back and do more with the previous 4 steps if necessary in order to answer the questions we had at the beginning. We will also take this time to back up our conclusions with the quantitative data and modeling that we have now created. So that's essentially the pipeline from getting our data to making our claims with backed up information. Next slide, please.
Before you move on, I just want to note that even though the steps do look sequential here, oftentimes, especially between steps 2 and 4, you're going to have yourself circling back. Because as someone pointed out, stuff does change as you keep on exploring and, keep on making discoveries with the data. You may need to, undelete a column you deleted before because you didn't think it was useful because now you need it, or you just want to explore another trend that you didn't think was useful before. But again, I just want to emphasize that this process is not very linear. It's a lot of going back and forth. So but yeah.
Also, real talk, you may think you'll spend most of your time on steps 3 and 4, you'd be wrong, but you'll be stuck on 1 and 2 for your entire lifetime.
Yeah.
Because as we all know, with real world anything, data is never in a nice order. And in fact, tidying it can actually be, as Samrat alluded to, tidying it and picking out what pieces of data are actually useful and what's corrupted or not usable in some way. That is honestly one of the hardest parts of doing any sort of machine learning, because that requires you to have some sort of experience and knowledge of what do I need and what am I trying to accomplish. And that can be very hard, just in general. So
Those are really important points. So when you do your project that we will give you near the end of the semester, don't be discouraged if you're trying to analyze stuff and realize, oh God, I need to go back and change a column or convert something in a different row. It's totally fine. It's almost expected that you will need to go back and change things about the data when you start an analysis. Totally fine. So Go on to step 1, data collection. We're going to go a little bit more in depth now into these steps. So, like I said earlier, this is the step where we're going to gather relevant data from reputable sources. So I'm now going to go into those two fundamental factors a little bit more deeply. Yeah, I know, right?
No.
Anyways,
Sorry.
anyways, factor 1 is about wait, hey guys, what's going on?
I was making sure we're still meeting.
Oh, okay.
Carry on.
Anyways, factor 1 is relevance. This is essentially referring to the fact that our data can every. I'll just like this. Everyone can hear us small. I can hear you just fine, Phil, but I don't know about the rest of you.
I am ending this man's life.
Go ahead.
So, like I said, with relevance, essentially, we're just making sure that the data that we are getting needs to contain all the explicit answers to our question, and can essentially actually answer what we are trying to figure out. Ideally, we should not have to make that many jumps in logic. Does that make sense to everyone, or would you guys like an example?
Or you all have a seat.
I mean, I'm kind of half the same too, so.
Yeah, I mean, I'm not gonna blame you if you are.
Yeah. All right. No, I think that's pretty fair. So. No. Okay. So for example, let's say I'm trying to predict the profitability of Walmart based on their toy sales, right? So I have some toy sale data, or rather, I do not have some toy sale data, but I want to use toy sale data of Walmart to predict how the profitability changes as a function of that. However, let's say I can't find toy sale data of Walmart. So I decide, oh, what I'm going to do instead is I have this data of toy sales in Target, and I'm going to feed that into my model, see the result, and try to extrapolate those results to Walmart. Essentially saying, oh, if toy sale data for Target can predict Target profitability, then the same applies for Walmart. That's a very huge leap in logic, despite the fact that Target and Walmart are very similar stores. So for our specific question of if toy sales at Walmart are a good predictor of profitability for Walmart, that specific data set is not the best. And that's kind of what I mean by we should need to select our data properly in order to make sure we're not making very large leaps in logic. Now, predicting specifically, I believe for our final project, we will be giving you the data set, and we will be telling you what question you need to answer, so it's not going to be that huge of a problem. But when you go out into the real world and the professional world, potentially, this is something you should probably do when you're trying to select your own data. Try to make it, essentially what I'm saying is try to make it as easy as possible for you. So you'll thank yourself later. That,
I'm not in charge.
I wasn't done.
Oh, my God.
This guy was like, I got you, man, but absolutely shit the bed.
Anyways, the second factor is reputability. And what that just means is that our data should ideally come from a trusted source, because if it doesn't, it'll be very easy for critics of your research paper or your project to point out like, hey, did you just like make this up like on your own, or did you get your friend to make up this data? So it's very important that we get our data from a trusted source, such as a government website, trusted institutions, or data aggregation websites such as Kaggle.com. Kaggle.com specifically is what we will be using in this file.
Note that just because it's on the slide, the trusted data source, government websites can be absolute garbage, as Soham and I will tell you quite a bit. Trusted institutions, Indeed.com is a trusted institution. Their data set, as Soham and I will tell you, is some trash. On occasion, it's accurate. It's just accurately shit. And then Kaggle, anybody can make a data set on Kaggle. That's like the one that like actually wants you to be careful of is Kaggle can have some like they make pains to ensure that the data that they put there is fine, but it's pretty easy to have some pretty sketch data on that website. So the point is like this kind of just goes with anything you download to your computer, but when you're working with this sort of stuff, make sure that like you scan through the data that you're downloading and it's not some sort of malicious anything. And moreover, since this is accurate, if you are specifically searching for malicious code, such as if you're running a model to try and identify whether or not a binary has like a virus in it or not. Don't run that on a personal computer, because that's gonna go very badly very quickly. Basically, just practice general cybersecurity rules of don't run things on your own computer if you don't trust it, and you should be okay.
That's a very good point. Always remember to do your due diligence, even if you are getting it from a relatively speaking trusted source. For Kaggle specifically, I believe people can leave comments about data sources. So if you find a data set you like, you can search down into the comments and then see what other people are saying. So if a lot of people, if you find this really cool data set, but a lot of people are saying, hey, something looks messed up, maybe skip it.
Yeah.
Another thing loosely related to what we're talking about is oftentimes when we have data sets that pertain to personal information, this comes up a lot in banking, as you'd imagine. It's very important that we find methods or just keep general practices to make sure that data is secure or encrypted in some way, because we don't want to leak a huge amount of data to anyone in the public. So, and the other thing is, concerns with privacy in general, social media is a big component of it, like, be able to own your data. So just keep that in mind. It kind of treads along the ethics side of ML and data science, but yeah, it's good stuff.
Yeah, actually, usually, if you're doing research, the IRB, which is institutional review board for this, don't know that is the group of people that control all research projects at like your institution, like what they're allowed to do. They will tell you how to handle your data, and if you deviate from their rules, you're gonna get in severe trouble to the point of either losing funding as usual or something like that. Having the least bad they can do is tell you that your research is bull crap and you have to like scrap the entire project and lose the time. The worst they can do is actually fire you because you were in clear breach of US, of the laws. That's not a great thing. But like usually you'll have some sort of thing like that. That will tell you how you're supposed to deal with your data in a research setting. In some sort of corporate setting, again, there are laws governing people's data, some revenue privacy, here's what the big ones. But like also like they are not as tight as you'd want them to be. As we all know, being tracked by Google and everyone. So like again, just be very, very, very careful. Like I can't stress this enough. Actually, be very careful with the data that you download, and don't just hit the download button on literally anything. It's like, oh yeah, I can make a model out of this. It's very easy to embed like malware into something that just looks like a big and has a Dutch extension on it. So
as a further point, I know as a personal example, Bill and I don't know if we mentioned this, we're on a gemstone research team where we're researching hiring bias in AI.
It can be biased for giving it, they just don't think it's funny if you want it.
But in any case, part of our research is that we have to download resumes of real people, not like simulated resumes, real people's resumes from Indeed to track down some information about it. So we have a database of all of this information. And if we decide to publish our paper or publish the data, we have to go through a very painstaking process of even like not even just a single anonymization, but a double anonymization, just to make sure no person's real info can be traced back to them. And if you can, we're going to be in serious trouble.
It's even worse than that, actually. We're already off on a tangent, so like I'll save it, but I think Minute Physics or 3 Blue 1 Brown, one of the two, have done a video on how the US Census specifically privatizes data. And like the point is that like there are a lot of ways that you actually do need to, like a lot of steps you actually do need to take if the goal is that the data set that you use needs to be private, but still useful for like machine learning or like analyzing trends in general. And you'll figure those out as you continue, but like the main point is that like the data that you do work with, make sure that you handle it the correct way. Because you can get yourself into some severe personal or like legal trouble if you mess up. Sounds a lot. I know you're probably thinking that it's not actually that severe for like most things. It actually is very interesting, but like yeah, it can get it's a very slippery slope in terms of how quickly your data set you need to start actually thinking about how private like the people that are in your data set are.
All right, I think we got the point.
What was wrong? Sorry.
Yeah. Good. There's a good drink.
Oh,
Of water.
no, my man is just chugging fucking beer back here.
You're not anyways, now we're going to go into a little example of the previous data science project that I have done. So who here has seen any superhero movie ever? And it doesn't have to be MCU because everything. Wow, okay, that's like almost everyone. Okay.
Yeah, extraordinarily popular, dude.
That's insane. Anyways, all right. Who has ever seen an anime? Anything at all?
Weebs, what?
Technically, you can have an anime movie that's also a superhero movie.
No,
I mean, I count Movie Train as that.
we do not.
Okay.
So for my 320 project, it's a course at this at the computer science department, which is introduction to data science. I would highly recommend taking it if this is something that kind of interests you, like stuff we're doing in this class. I would personally recommend Jose Calderon, who's still teaching it.
Dan Dickerson.
Dickerson's amazing. Yeah.
But in any case, for the not the remainder of this lecture, but at different parts of this lecture, I will go through different parts of this project. You can kind of see what the data science pipeline looks like in a real instance, rather than just as high level concepts. So for this project, basically what I was doing was I got data on superhero movies and anime movies, and I was like, hey, I want to compare the two and see which one is more successful overall. And I essentially said that I was going to measure success with a variety of methods in order to make things more comprehensive and holistic. And just as a general note, if you are comparing multiple things and trying to find which one is more successful, it will help you immensely if you define for yourself in the beginning what you mean by success, because success, even in the same context or the same situation, can mean a lot of different things to a lot of different. That's something I just would like to point out. Okay, so for now, I will just go over the data collection portion. So in this first code block, these parts particular may look a little bit familiar. This is what we have been doing last lecture, just importing pandas and NumPy. In addition, I imported a few other packages in order to help me with the analysis portion of my project, which we will see a little bit sooner. Next, I just have a little description up there about where I'm getting my source from. So I got mine from Kaggle.com, as we said earlier, it's a data aggregation website. So up there is a little blurb about what this data set is, what is the information in the data set, and a little bit about why I believe it is reputable. So up there, I said that the data set was provided by someone who is a master science student in data analytics from a widely known university that is known worldwide. He was from National College of Iowa. Okay. But in any case, that was kind of just me doing my due diligence to make sure that the data set was reputable and the data set was coming from a reliable place. Not listed up there, but I did also look through what other people's experience with the data set was, and they also had mostly positive experiences. So from those two factors combined, I was able to conclude that this was a trusted data set that could be used for this project. So additionally, now that that blurb is done, we can actually get a little bit into manipulation. But to get there, we must first load in our data set. So here I'm using a pandas command called read CSV. A CSV, for those of you who don't know, is just common separated values. Sorry, it is just common separated values. It's a special type of file that a lot of data sets are stored in. So this powerful command will just take the CSV and read it in as a pandas table, which is very helpful because of what we mentioned earlier about how pandas tables are very powerful data structures that can be used to very easily organize data. As we said earlier, we can use the .head command on a pandas table in order to look at what we have in our table at the beginning. So this is what our tables look like without any sort of manipulation at all. So this is just a table of ratings from IMDb. And this next one is a table of the names of the movie along with some other information about them. So that wraps it up for the data collection portion. Does anyone have any questions that they would like answered? Anything you'd just like to know more about? either from here or the Zoom. All right. So we're good. Yes. What do you think?
Okay, so, quickly, why do you think we need to clean data? You know, give some, places where we need to clean data. Like, there are some things that can go wrong with the data set that we have to clean up.
If you're in the Zoom, feel free to answer as well. The Zoom chat, bro.
All right.
Yes.
If you have an outlier,
Yeah.
Sorry?
if you have an outlying point. Data point.
Potentially.
But also not. I mean, in a way, you're right. But also, if your data is an outlier, that may actually be valid, useful information as like, small little like corner cases that your model needs to look into. So I'd say like you're right about like 60% of the time. But like that other 40% happens to be where I work in. So. But like, yeah, that does pop up. The other 40% does pop up.
It depends on a context, like,
Yeah.
if your values mostly range from like, say, 1 to 10, and you have something like 1 million for one coin, then yeah, maybe that's probably something you want to get rid of. Because that's probably an anomaly.
Yeah.
Or someone manually entered that incorrectly, yeah, sure, any more takers? Any more examples of define useful trends? Well, that's actually actually an outcome of EDA. So,
Yep.
I would say that's more of an outcome of EDA, exploratory data analysis, finding trends.
I would agree with that assertion.
But
It is a good reason why we need to clean it. Because
Yeah.
we can't do that without cleaning it.
that is true. Yes. More examples, please. Yes,
Maybe like you don't have enough data to say anything meaningful about it.
sorry,
Like you don't have like enough to say anything
you
meaningful,
don't have enough data,
like for like a problem set.
right? That's fair. But like, let's say
really be cleaning, but that would be more like that would be more EDA. Then you have to like try and create something out of nothing.
yeah, this is more pertaining to like the data you already have on hand.
What are specific things that you like if you have a data set that you want to get out of it?
Yes,
Excuse me, some data could be like incomplete, it's just like not like fully fleshed out.
That's a very common one.
NaN values.
Yeah.
Wait, I should probably ceiling NaN values on you.
Well, NaN, for those of you who know, NaN, that's actually, of course, for those who don't know, NaN means not a number. It's a common programming term, or just something that's a null value. Because like null is like a valid thing to like throw in like data set if it's like there's literally nothing there, and like null or 0 is usually the same thing. But if it's like not a number, or like it's like an empty cell in like an Excel spreadsheet, then like that is something that like you have to make a choice about how you deal with that. Commonly we do kick them out, but if you think of, say, if you're trying to get data from that's like, say you're trying to get like data through like Twitch, like through like a live stream count, and like or like a number of people watching on the live stream, like you see you're tracking that as the stream is happening in real time. I think television probably does that to see how many people are tuning in. If you're trying to analyze that, I mean, computers fail all the time. There's going to be like a gap in your data where like some bit got corrupted or some package didn't make its destination. And so you're gonna end up with a null value there. Well, you have to make a choice then. Do you want to just drop that time point and say like, oh, okay, we've got an issue? Or do you like, interpolate it? You do like, okay, well, we know it was that like 10 seconds before, and we know it was this 10 seconds after. Let's just like take the middle and go with it. But yeah, like null values often drop, but not always just entirely like dropping credit.
And that goes into an interesting point about missing data in general, because in real life, there is a lot of missing data. So you often, like, as Phil mentioned, you have to drop them at this question. So do I delete all the rows that have missing data? Or do I do this thing, one method called imputing it, or replacing the data with, reasonable value? We'll get to the more specifics of that later, but it is a very interesting question, and it really depends on the situation, which the two options you choose to deal with this data, because the reason you don't just want to delete data is that you want as much data as possible. That will make it generally, it will make your machine learning model better compatible. But yeah, I think that's
All right, after that lovely intro from Samra, we are now going to get into the data tidying. So just a reminder, data tidying is just when we remove or manipulate our data set in order to make the data within it easier to work with. So here I have simply listed a few examples of what data tidying can look like. I know that this looks like kind of a lot, and you might not know what all of this even means. Don't worry, like I said, the data typing step is arguably the step that varies the most with regards to each data set, as what you do in this step is going to vary wildly depending on what you're trying to answer with your data set and how your data set currently is. So here are some examples of what you might need to do. You might need to join two tables together based on a certain attribute. You might need to remove some irrelevant data because you don't want it. You might have to change the type of a column. So let's say, let's go with someone's example where we're getting TV ratings in from a live source, but for some reason we get them as strings. That's not good, obviously. We're going to need like integers or floats or something. So that's one example of where we need to change the variable type. We might need unit conversion to get everything in a standardized type. We might even need to reset indices to make sorting easier in the future. And we might need to even make new columns. So just to make it easier for us to analyze. Also, as Samar was saying earlier, as an alternative to dropping or removing irrelevant data, we might want to impute the data, which is essentially where we use the past and future data that is already in the data set in order to predict what data should be in a specific row at a specific time period. We will not do imputing data today, but we may cover it at a future date. Next slide, please. All right. Let me show you what data tidying can look like. So this is the data tidying step that I chose to do. So essentially what I'm saying is that even though we have the data loaded, we can't directly jump into analyzing it because it is not optimally usable. And all that means is that it's not in the greatest state that we need it in. And if we try to analyze it right now, it would actually be like very hard and annoying. So instead, we're going to do some stuff on it first. So here's one example of data tidying. We're going to join the data sets. So just as a reminder, we currently have two data sets, right? We have one with the IMDb ratings of all the movies and one with the names of all the movies. But one big issue is that when we're analyzing, we don't want to be cross-referencing two data sets. It just gets really annoying. And not only is it annoying, it can actually open us up to various errors if we're not careful about how we reference each data set. So what we're going to do instead is do this join operation. This is a standard operation that you can do where you select two data sets and then you're essentially going to join on a specific attribute. So here we're joining on something called the IMD title ID, and if I remember correctly, yes. So as you can see, both data sets, since they're from a very similar source, actually both have this one called the IMDb title ID. It's essentially a unique numeric ID given to each movie. And since they correspond to each other from both data sets, we can join on this attribute. So once we call the join operation and then do data.head, as you can see, the two data sets are then merged together with the data from both. So we have the rating attributes and the name attributes, which is pretty nifty. It's great. Additionally, data typing can also involve renaming columns, just to make things easier for us, or renaming certain attributes. So here I just like renamed some of these titles, made some of these things shorter just to make it easier to analyze. More importantly, though, I like to get into column dropping. So this is where we have certain attributes that I know we're not going to need during the analysis. So this is so first what I did was I just returned all the columns we have. Yeah. This is what I started out with. It's a lot, as you can see. And essentially, while it's true that we always want more data, we also need to remember that we need relevant data as well to answer our specific question. Additionally, if the data set is too large, it can actually slow down our operations, which is very not good. So what we do here,
Keyword that exists.
I don't want to use it.
Alright, this is some like new speech, but sure.
Yes. Bill is actually an old man, he did not caught up with the time, people have to forget him. But in any case, no, it's fine. In any case, so here we're going to use the drop command, where we can put in the titles of the columns that we want to get rid of. And we are essentially just getting rid of all of these columns because we do not need them. And like we said earlier, this was not a singular linear process. It was a lot of back and forth between this and the analysis step to determine like, okay, what columns do I need to drop that I actually did not drop? Or alternatively, if there was a column that I dropped previously and I was like, oh god, I actually need this, I need to go back up and redo this entire command. So again, it's a very, even though we present it as a pipeline in order to streamline the learning process, the pipeline of data science is very circular and will often require a lot of iterations to get correct.
Also, if you're wondering if there's a more efficient way to drop all of these columns at once, no, there's not. So I mentioned you have to drop one of them, go back in, like, okay, cool. Drop the other one, you have to literally type out the names of every single one. You can imagine this get very complicated in data sets with over 100 columns. It does. I won't get into the specifics, but it got painful.
Oh yeah, it did. The only nice thing is that with the pandas drop command, you can put every single column into a list. So if you're dropping like 50 columns, you don't need to call drop 50 times.
You need to make a list of 50 things.
Exactly. So that was the main aspects of data typing. So I'll just quickly go through these. Here we were essentially I'm essentially changing one of the columns, and for example, this is what I was talking about with the unit conversion, or not the unit conversion, the type conversion. So I have a year column of when each movie came out, and I want to use that in my analysis. But the problem is that it's all strings. And if you guys know anything about data science, you might know that we can't really do numeric analysis with strings. Or at least not the ones we want to do. So I have to change everything. Yeah. So we have to change everything into a numeric format. This is a similar process to earlier, where instead of dropping columns, we're dropping certain rows that we might not want. Some for various reasons. Some of these are not the rows that we are looking for. Some of them are actually duplicates. And additionally, this is also where we are defining what a superhero movie is. And essentially dropping all the, we're dropping some of the rows that do not fit this definition. And this is kind of just what this looks like. And we are also, in this column here, just defining what an anime movie is. So we are essentially saying that an anime movie is any movie where the country of origin is Japan, and the genre for the movie contains animation. And this was our best way of defining anime movie at the time. And this is how we define one of our major categories. Finally, this is again something else I mentioned of the type conversion. So all the anime movies, as they are made in Japan, they have all their monetary info in yen. And if we're comparing to US dollars, that's not very convenient. So we just convert all the yen into US dollars. Here are some additional column manipulation. If you guys would just like to take a look at that. Like I said, this project does not cover imputation. And this explanation is essentially saying, hey, for this specific project, I don't believe imputation really makes sense in the specific context. And we are not going to do that. That's essentially what that's saying. So next up is EDA.
Actually, can I use mine? Do that time for one more time?
I'd like to get to the presentation. We are almost to the, yeah. If we have time at the end, though, we might go with that.
No, it would not be appropriate for this specific one.
So here's step 3. It's explanatory data analysis. Again, just a quick refresher. This is where we're going to cross-reference our data with each other and certain models in order to find trends and, importantly, visualize a trend in certain graphs to make it easy for people to see what you're seeing. This is really like the meat and potatoes of the data science pipeline, excluding the AI stuff, because this is where we do our actual analysis work. So with this analysis step, we're going to be doing various steps in order to find the trends in our data. So we're going to be finding those correlations by conducting certain correlation commands. We'll mostly be using linear regressions, but we can use other ones as well if we want. We might also check the frequencies of different values. And we will also access data balancing if we are going to do AI modeling. Just as a quick aside, data balancing is where we might be trying to sort data into two disparate categories. Let's say, I don't know, we're organizing people who have heart disease and we're trying to predict if they're going to die or they're going to stay alive.
Oh, that sounds very eerie.
Yeah, it's crazy if any of you were here last semester.
Yeah,
But in any case, actually, who was here last semester?
literally none of them.
That's fine.
There were all 5 people last semester.
That's fine.
I mean, that's good in a way,
Yeah, no, I'm happy, there's more.
100% covered.
But in any case, one problem that we found with our heart disease data set is that there were significantly more people that were alive than were dead.
Yeah, that's a problem.
Yeah, obviously that's a good thing, but for us, that's a problem. Because we found that data is valid where there weren't enough people who died. So,
So you see what someone did, is he started the McDonald's in every town he could find, and just shoved it down everyone's mouth.
so the two ways we correct the problem are either A, kill some people with heart disease, or B, significantly more ethical and logical method, which is where we use state-of-the-art algorithms such as smoke, which is an oversampling technique, or undersampling techniques, in order to create or destroy data, in order to make sure that the balances are equal, per se, essentially making it so that there's about an equal amount of people who have lived or died. We'll go into that a bit more in our AI lecture. Additionally, another big part of EDA is graphing our findings. So we don't want to just do cool data science stuff and just like play with our code, right? We need to actually convey our results to the public. So a big part of this step is not just executing commands and algorithms, but also drafting what we find into a way that is very easy for non-computer science or non-data science people to understand.
Oh, also like that is really interesting. One of the things that like I would say is like it's kind of like actually being used in data science. Know how to use like pick like a graphing library in Python and learn like every single thing about it that you can. Because like the one thing that is always that people always want is colorful, nice to look at graphs. And if you're unable to make one, your work is honestly fucking useless because then they have like genuinely because then they'll look and they're like, ah, that's great, cool, linear algebra. I don't know what the hell that means. I took that class in college and got it. Like, you know, for what's important is showing them that hey, this is how we compare it to something else, this is what the model looks like, this is how it behaves under this, so on and so forth. And we'll genuinely show them this is why what I'm doing is important in some way. So like knowing how to graph things correctly, which some will really talk. Yeah, but like just in general, knowing how to graph things correctly is like one of the most valuable things because it is extraordinarily important just to making your work do anything useful.
Exactly.
That's also a very good point too, because sometimes, depending on the business context, you will often choose a model that is more explainable to the public or to the government.
Not sometimes, every time.
Yes,
Generally,
those
every
are
time.
yeah.
it does.
So for example.
So my research is actually on specifically
Oh, really?
choosing a model. Yeah, so the research that we do is on bias in hiring software. And part of the work that we do is to ensure that, hey, if you're going to make a model, you need to explain that, hey, it isn't biased, and you need to show like why it's not biased, in what way. And if you're going to claim that it is biased, like we are doing, we have a lot of graphs, lots of numbers to back up why we're saying that, but you need to have the graphs and the numbers and all the analysis that tells you this is why you're making this claim. Otherwise, you can't really, otherwise data science has no purpose because then you're just doing stuff with no real reason for like why you're doing it.
All right, next slide, please. Sure.
I mean,
My bad is just like dancing at this point.
All right, so here I will go over the data analysis that I did for my project. So, like I said, we have our superhero movies, we have our anime movies. Our goal is that we're trying to figure out which one was more successful. But what do we mean by success, right? So one way I defined success was through ratings. I think that's a basic way that many people would define success for a movie. So I was like, hey, I want to analyze the greatest scores of both the superhero movies and the anime movies. And the way I did it at first was by creating this chart of the score breakdown, specifically a pie chart. So here I'm just creating some bins, and what that means is that these are essentially kind of like lists that are going to have each score that corresponds to a certain category. So for example, there may be one category that has everything from 3 to 4, so another category that's everything from 4 to 5, et cetera, et cetera. So we have all these bins, and I've separated by anime movies and superhero movies. So yeah. Here, to illustrate the point of data visualization, here you go. This is the score breakdown of both categories. It is very accurate, very correct, but as you can see, it's very hard to get any sort of conclusions from this data without like doing some significant analysis of it. So let's make it pretty, right? So here we're using the .py command, which I believe is from matplotlib. And we are essentially just putting them into pie plots with these nice little titles and labels. So here we have the breakdowns of both the anime movies and the superhero movies by their basic scores. So now that we have the actual graphs, what are some observations you guys are seeing between the two categories?
Most movies are rated at 7.
That is correct. That is true. For both anime and superhero movies, most people would give them 7s. And that makes a lot of sense, right? It's a very average score. That's what most people are going to give it. What else would be
What is the pie chart?
the pie chart still?
Yeah. I'll save my comments.
Is there anything else that we are noticing about the breakdown between these two categories? Yes.
Oh no, the superhero movies have like higher 8.5 rated rating. The higher percentage.
Yes, that's correct. They do tend to have more of the highs.
There's not a lot of weight.
That's true. So essentially what I'm saying here is just a preliminary of what's to come. I'm essentially just breaking down what I'm seeing in these graphs, where we see that the anime movies have a higher percentage of movies rated 6 to 7.9. And while the superhero movies have higher percentages of movies from 3.5 to 5.9 and 8 to 8.9. And essentially what I'm concluding is that superhero movies, for this data set at least, have higher highs, but also higher lows, while the anime movies tend to have greater consistency. Additionally, this is another data analysis where we essentially are looking at the score through a histogram. So this is another thing you might do, where you might analyze the same exact data and trends, just through a different method, in order to see different trends and to see if there's any bias, which can be very significant.
Just you dropping this.
Yeah, clearly. So this was essentially a similar phenomenon where the superhero movies had higher percentages of high scores, but also low scores, while the Japanese anime movies were more consistent on 7s. So here I'm moving on to another measure. So I looked at ratings, so I was like, gee, well, what about like monetary performance, like box office? And so this is what is being analyzed here, where we're essentially getting rid of the. This is another example of how the pipeline can often not be in discrete steps, where this is technically considered like some sort of data tidying, where we're getting rid of all the non-null entries here. And we are essentially dividing the data set based on if it's a superhero movie or an anime movie, and getting its year in budget. And here we have a bunch of scatter plots where we are graphing the budget, the US income, and the global income over time. So just quickly, only looking at budget of both. So for this graph over here and this graph over here, what are you guys noticing about the graphs? Yes.
the superhero movies have a much bigger budget than the anime.
Yes, that is correct. They do tend to have higher budgets. That is a point that I also was able to know as well as a result of these graphs, which is why it's important to look at various avenues. So here I'm just again putting in a little analysis indicating that the superhero movies not only have higher budgets, but they tend to perform better at the box office. That is true. That is something, that's again another factor that you're going to have to go into. It is something I explain a bit later.
Okay.
Yeah.
I was just curious.
And essentially what I'm concluding is that the superhero movies have seen greater market success over time compared to Japanese animated movies. However, as we know, superhero movies do tend to have very inflated budgets. So for one question I asked was, hey, maybe the anime movies are just using their limited budget more efficient. So maybe they have less budget, but they're still breaking in more in comparison. So what I did was I plotted the budget versus the local income. And this is what I ended up with. So what we quickly come to realize, especially if you look at the scale, is that the anime movies tend to have much better budget efficiency, given how they even have a few high outliers. But the majority of their data still has better budget efficiency than most superhero movies. And this is why it's important to mix and match different parts of our data in order to uncover the whole story. Because if we stopped over here, we could have just said, oh, well, it looks like superhero movies just have better budget and better cash rating, and that's the end of the story. But it was not the end of the story when we looked at budget efficiency. And that's why it's important to analyze your data from different angles. Here, I'll just speed through this a little bit more. This is where we did some hypothesis testing with the box office performance in order to ensure the veracity of our conclusions from earlier. These are the scatter plots I generated. And all of this is just a lot of statistical nonsense. Well, not nonsense, but it's a lot of statistics in order to just verify our claims from earlier were in fact correct. Again, this is just looking at the residuals and making sure our assumptions that we made for the statistical analysis were correct. Okay. Let's go on to step 4, AI modeling. So just to reiterate, this is where we're going to select, train, and improve on the AI model that we made for our specific data. Specifically, what we're doing here is we're using the results from the previous pages to guide what models we are going to use. This is very important. And one thing that we're going to stress very much in this book and in future lectures is that AI modeling is not just about looking at the shiniest or the most used AI model and just chucking in our data and producing the results. We have to fine tune our AI response very specifically based on our needs and our data. The modifications that will be made to our data are going to be vital in determining what AI model we're going to use. And hey, our data will determine if we even need an AI. Because sometimes you just really want to use AI for the heck of it, and it's not actually valid in that specific case. And like we said, this is such a huge part of the pipeline and of modeling in general. We're going to go into much greater detail of this part in future lectures. But I just want to mention it here just so it's in the back of your head. Next slide, please. So, final step. This is where we're going to draw our conclusions. So we're going to use all the information from the past 4 steps. We'll even go back to the previous 4 steps if necessary. And we are going to answer the initial business question that we had at the beginning. And now, unlike at the beginning of the process, we are much smarter, we're much wiser as a result of what we have done. We're going to back up our conclusions with the quantitative data that we have. It's true, this is not necessarily as splashy as the other pages, specifically with the data science and the AI modeling. But I would argue this is essentially the most important stage of the pipeline. Because similar to the data analysis stage, this is going to ensure that the average person will actually understand the conclusions that you created and actually trust what you have done and your process. It's very important to extrapolate your results and to specifically state what they mean in certain contexts. So we don't want to just say like, oh, we had a p-score of 0.01, or oh, this is what our value was. No, a big thing about this thing is we're going to contextualize our values in a real world context. Think of that. Just one more. Was it the example?
I thought I haven't seen MC on one of these slides yet.
I was really. So again, your conclusion doesn't have to be too big. If you don't want it to, but we do want to make sure that we're summarizing our findings succinctly in order so that everyone reading our project, even non-CS people, even non-computer people, can understand what the heck just happened. So here I'm essentially defining that superhero movies did win several of the metrics, such as rating, budget, and overall income. And I contextualize this to determine that they have a very bright financial future because their box office performance increased, or rather their box office performance increases the most over time. English is a very hard language as I say that. However, it's also important not to bias our findings based on what we want to hear. So for example, when I first made this project, combating superhero movies or anime movies, I was really hoping for like one of the categories to beat out the other in like every single category in order to make a more headline, yes, a more sensational thing, like, oh, superhero movies beat out anime movies in every single way possible for the entirety of time and space. But that's not true. That's not actually what I found. I found that, for example, the anime movies, while it's true that they have less budget, they have much better consistency with their ratings, and as well have better budget efficiency. So they can't be counted out entirely here. I also have this in final takeaways column, where I essentially mentioned that, hey, I think the reality of the situation is not that one is better than the other, but rather that both genres and both ways of making movies are just simply better at different things. And it's important that we have this nuance in our conclusions in order to make sure that the general audience is getting the full picture of what's going on. And speaking of conclusions, that concludes lecture 3 of Big AI. That's all we got. Does anyone have any questions, both here or in Zoom?